Darren Tapp. I'm presenting on math education in the Free State, and I know there's this project that's running around, but that's actually kind of a double entendre. The title should be Math Education in the State of Being Free, right? That's what it is. That's really what I want to talk about. I mean, what I've been doing happens to be in New Hampshire, but I don't think it certainly is restricted to any geographic location. Okay, so a little bit about me. I was born in Kentucky. I was interested in science and math at an early age, and so I ended up getting a physics and a math degree from the University of Kentucky, a couple degrees, and I got a PhD at Purdue University in math. My specialization was in algebraic geometry, so that was something I enjoyed very much. And currently I have teaching experience at 5 universities and colleges. So that's kind of where my background, that's where I'm coming from. I am a college professor, currently an adjunct. So here's some of the results that I've noticed being in a college. The people who come and enroll in college, often they'll take a math course, and I see that there's a high demand for remedial classes. And of course, now they call remedial classes developmental classes, and I've just been seeing a reduction in instructor autonomy, where it's no longer my class. It's a class it's somebody else's class I'm delivering. They don't leave it up to my discretion as much as they used to. And another thing, thank you. So another thing that I see is, let's see this. Bottom. Yeah, math anxiety, right? There's a lot of math anxiety that comes out of public schools, more or less, right? And so that's a question that's just, I think it should be at the forefront of a lot of people's minds. Why? Why is there so much math anxiety about math now? Okay, so hier wir haben die Blumen und die Katze, und sie sind sehr schön, ja, und wir haben eine Blume hier und eine Rose, ja, eine Rose, ja, und hier ist die Katze. Warum sind Katzen die Meister der Internet? Wir wissen, dass Katzen die Internet gehören. Ja, wir alle wissen das.
Sehr gut, ja.
Now, how did that make you feel? How did our discussion of cats and flowers make you feel? Just think about that for a second, okay? It was a little weird, I admit, but how did it make you feel? Now, this is an example of a nodal cubic, and at the bottom I have the equation that defines this nodal cubic. And you can see it's an algebraic curve, and it crosses itself at the origin, and that point where it crosses itself is called a singular point, and this particular singular point is an example of a node. Now, when we're dealing with singular points, sometimes we'll blow up a point in the plane, for example, and so this is in a picture, it's a blow up of a point in the plane, and you can see how there's this bigger space that kind of projects down into the plane. And then the singular point of that nodal cubic would actually hit that line above the point that's blown up at 2 different places. And so that's one way that algebraists at least deal with singularities. And singularities can be more complicated. So this is an example of a surface that has an E7 singularity. How did that discussion make you feel? Right? All right. Should you have felt any different? Okay, now maybe you have a math background and this wouldn't apply to you, but if you don't have a math background, what's the difference? I'm speaking German, I'm telling you about some singularities. They're both just pretty pictures, right? That's really all it is, right? They're pretty pictures. You either understood the words or you didn't, and they're pretty pictures. But I would assert, this is kind of an experiment that we're doing right now, I would assert that you shouldn't really feel any different compared to one or the other. There was some information you may or may not have known, and shouldn't feel any different. So what would math education be like in the absence of the state, or in the absence of the government? or the absence of institution that monopolizes education? Well, I'm going to tell you that I don't know. Okay? I'm an academic. I haven't really studied this problem so much, but I would expect there would be more variety. Clearly, almost there has to be, because it's not just one size fits all. Okay, so to investigate this problem, I started what I call Dr. Tapp's mathematical playgrounds, and I actually started in November 2014, so I was able to present last Liberty Forum. And I offered parents math activities for children age 6 to 9. That was my target. I always advertised targeted. And I started with 2 students and quickly had 3. And most recently we have 7 students. And that's since November, so that's some growth. And after a break in March, April, I'm going to offer 2 levels in May. I'm going to switch from 1.5 hour level to 2 separate 1-hour levels. So, and now in September 2015, I offered parents an algebra and trigonometry course, ages 13 to 16 target. I started with 5 students, I now have 6, and because of the nature of an algebra course, I don't expect this course will grow very much because algebra is cumulative, okay? So I'd have to start another course in order to reach more students. That's what I would expect. So early on in this project, the project of Dr. Tapp's Mathematical Playgrounds, this is some work that was done. I was telling kids about Pascal's triangle, and a student initiated making Pascal's triangle again. She would make it several times. I mean, maybe 2 weeks later she'll make it again on her own without me reminding her about it. And I was really wanting to work on an algebra curriculum because that's really where that's really what I love. So when I found this book that has Pascal's triangle on the front of it, and it's also by Gelfand, that's an author that I read some of his work while I was in grad school. So it's a real mathematician. It's a book that's for high school level. It's got Pascal's triangle in front, which is what I'm teaching the kids. And it just seemed like it was a great fit. I had to order it, and it passed my inspection. So this is a book I'm using for an algebra class. One little point of note is that this triangle with these numbers, all those numbers are binomial coefficients. So I've been telling 7-year-olds how to make this triangle, because all you have to do is add the 2 numbers above. So I figure that's at a 7-year-old level, because all you do is add. And I'm giving 7-year-olds the ability to understand, or at least know what the binomial numbers are when they're 16 or 20, or I think it's funny if they end up in a statistics course, they might think back to, oh yeah, I remember that. This is an example of some work a student did. For the young people, I don't really have homework, but this student just decided she wanted to take 1 and double it and double it and double it. So this part of it's cut off as 8 plus 8 equals 16, and then 32, and she just did this on her own. And I mean, I know she did this at least twice. One time she was correct, one time she was wrong. But she went all the way to 4,184,304. And this is something she just did on her own without too much prompting. But this is also an example of a geometric sequence. So it's something that exists in math in general. And I just want to give you some ideas of what I do. I asked the students to make factor trees. These are, usually I would just write a 10 and then write a 5 and a 200, but we built it out of poster board or cardstock and yarn. We built our factor trees, right? I always try to make it as hands-on as I can if it's possible. And this was in the same series. We made what I'm calling a factor forest, for the kid-friendly name. But when I was thinking about this project, I called it the spectrum of the integers. That's what I was thinking about it in my head. And then actually I tried to Google a picture of the spectrum of the integers, and I didn't really find the picture that I had in my head. But anyway, this was a lot of fun. So I took styrofoam and coat hangers, And I had the students make the prime numbers 2, 5, 3, 5, 7, 11. And then above the 7 and 11, we can put 77. So above the 3, the 5, and the 7, I think there's 105. I put the least common multiple of those three numbers above it. And something really interesting happened during this project. There's a, I think he's 7 or maybe 8, you know, their ages change. I said, hey, here's this styrofoam, could you put a 15 on it, right? And well, that's above the 3 and the 5. And if you look at this picture, he didn't write 15. He wrote 3x equals 15, which is an example of an equation. He's like 8 or 9 or 7, I don't know. And he's at an age you wouldn't expect this to happen. And I was thinking, he's just writing that down. He doesn't know what he's writing. And I said, well, what's the solution to that? And he said, he correctly stated that 5 was the solution. So he has some understanding of what he wrote. And I was running out of styrofoam, so I couldn't make another 15. So I just, when we were constructing it, I could, okay, we'll take Patrick's artistic interpretation of 15 and put it right here. That's what it is. But, and this is an example of, well, I wasn't really encouraging algebra for the young people, but a parent was, and so it spilled over into what I was doing. So I'm actually encouraged by what that might mean. So this is an example of art added an elliptic curve. I drew an elliptic curve. I drew that with just the basic shape, and they added hair, a bow, eyes, mouth. You know, they made it look all happy, right? So does this look anxious to you? Right? No. But one reason I really like elliptic curves is because JJ and I have a podcast about Bitcoin that uses elliptic curve digital signature algorithm, so it's a lot of fun to think about. Another station I have is I bring gumdrops and toothpicks, and I invite the students to build anything they want. I first say, hey, do you want to build a cube or something like that? And maybe they'll build a tetrahedron or a cube. And I show them all the Platonic solids. There's only 5 of them. And these I built for myself. This was set up before all the students came by. But then they take their gumdrops and toothpicks and build things out of them. So this is bringing geometry to them in I think, a reasonable way at their level. It's hands-on. This is an example of Mobius strips. So one day we made a whole bunch of Mobius strips, and you can see how they colored them the way they wanted to color them. I think it's important to have that level of expression that happens. So there you go, 7-year-olds building examples of non-orientable two-dimensional manifolds. That's what they did, but they don't know that. Anyway, but I do give them the term Mobius strip because that's what it's called. And they'll pick up on it, and they'll use the term, and that's the actual words for it. Here's an example of Fibonacci spiral. This is a great little activity because first you get to introduce the Fibonacci sequence, and that involves addition. So you get to practice your addition again, and then you're going to got to draw a spiral to see the sequence in a very real way. This particular picture, the student added another page to the page he was working on. This is not uncommon. They'll do that on their own. I don't have to say, hey, put another page there. They'll ask me, hey, can I take another page on there so we can keep going. This is a multiplication table that they made pretty recently. This is something they do often. So this time I took the blank newspaper and put it on a board of wood. And that was their palette to make this. So I try to make it a little bit different than they usually do. One thing about with the young people, I don't really have tests or anything like that, and that's on purpose. And there's no assigned homework. There's no homework. If you don't get it done, it's horrible or anything like that. But one thing that I noticed is they can do an activity like this. They fill in the multiplication table. And then I gave 2 students different color markers, so then I know who did what. So they're doing a group activity. I'm able to assess how they're doing and what they know without a test, without a grade, without whatever, right? And it's a group project too. I know who did what, and it's just very natural the way that works out. And this is something that happens occasionally. I encourage them to write on the board, so they got a little bit crazy with this, but I told them the elliptic curve became the sixth person. I'm talking about elliptic curves and lines at the top right. And then I had to, somehow they asked me a question, so I told them something about a tangent line, which is way above what a kid should know, kind of, but why shouldn't they be exposed to, right? And one of an 8-year-old actually wrote the word tangent line. Let's see. Yeah, there you go, tangent line right there. She just writes the words. And so I think that's pretty good. I'm not expecting them to do calculus right away. And tangent line is a concept from calculus. Here's some cones. Back to the geometry. The student decided they would make a cylinder as well. Anyway, then the students, we did the Pascal's triangle again, and they always add their own little twist to it in strange ways. So we made Pascal's triangles in January, and so one of the students said, let's make Pascal's Christmas tree, and so they all made Pascal's Christmas tree. So I think that just having these types of activities helps lend to creation or to creativity and things like that. So here's an example from what I'm doing in Manchester. One student just wrote "I love math" on the bottom, and this is a different student than the one that was writing "I love math" last year. So I actually had a repeatable result. I was really surprised. I was really surprised at that. And I don't know where this came from, but you can see we're talking about millimeters and area, and the student's handwriting is actually better than mine. I think she's 9. But and then they explain. She explains what she knows to other students, and that's how. I mean, it's kind of there's some free form going on. I have the students. The last slide was dealing with measurement. I have the students measure distance and time, so they have meter sticks and they have stopwatches. And so this student just started drawing a picture over here, and I had no idea what they were drawing until they were close to the end. They just drew the stopwatch that they were playing with. Okay, so I mean, we could sit about and argue the academic merit of this, but they're engaged and they're looking at it. They're conscious about what they're seeing. This is a game that the students made up where they were hitting an eraser. This is kind of an organic thing that happened, and so they were hitting it against the other rulers. This was not my intention when I gave them rulers for this to happen. But then I try to explain that the eraser would hit the ruler at different numbers. And then so they changed their game so that if they hit the number, that was their score instead of just a 1 point. And so now they had to add the numbers. And so even though it's kind of a crazy deviation from normal math, now they're adding numbers, right? So and it's a way that you don't have to say, okay, sit here for 2 hours and add all these numbers until you do all the ones on the sheet, right? It's just like, oh, now we need to add these, and they'll actually stop playing the game and add the numbers, or try to, or I can explain adding them, or it's whatever we need. So after a year, I think I can report on some drawbacks, and I'm a bit of an academic. I would like to actually report that everything's perfect, and I know how to do everything right, but I am an academic. So what are drawbacks of what I'm doing? So logistics of what I'm doing. I have to find a meeting place, parent schedule, having homeschoolers meet at the same time is quite a task. And just organizing these things in general is a drawback. Another thing is divergence of levels. As a student might enter and a student might leave. Like I had students join 4 months in. So the students that have been there 4 months have had experiences that I know they've had that the newer students haven't. So that's a drawback of what I'm doing. Okay. Of course, I could try to fix that by only having one set of students and not letting people come in and out as they go. But then I don't know. Then getting enough people together might be a problem too. And scalability. I was saying that I'm up to 7 students, but it's becoming clear that the scalability is going to be an issue with the young people. Basically, they can get rambunctious. And it's hard to keep everybody at the same attention on the same thing. So up to 4, it's easy, or up to 4 it doesn't seem to be too much trouble. But once you start getting above 4, at least with what I'm doing, they get kind of rambunctious. Okay, so another thing I wanted to mention is that philosophical topics are okay for young people. Here's an example of a 9-year-old's interpretation of the allegory of the cave. So, I mean, in Plato's Republic, Plato describes 2 people that are chained in this cave, and they're looking at these shadows, and they think those shadows are all there is to life. But then somebody comes and frees the 2 chained people, and they go out and they see that there was a fire that was casting shadows on these other people that was casting the shadows on the cave wall. Okay, so I told this to a 9-year-old, and they drew a picture of it, right? So that's okay. But with everything I've been teaching, every time I teach, I find myself almost always talking about this allegory of the cave, because sometimes I think of the number 2 as kind of existing on its own, right, outside of the cave. And then when you think of the number, it's just kind of the projection. Like when you have 2 in an object, it's just kind of the projection of the abstract 2. So I think there's a lot of things about abstraction in the allegory of the cave that I found that if I tell high schoolers, they think it's interesting. If I tell college students, they think it's interesting. If I tell kids, they draw nice pictures. So reflection on the arithmetic part of what I'm doing. Maybe, so when we're dealing with math education, maybe focus should be taken off of algorithms to multiply and divide. Okay, I actually think the algorithm to add is great because they pick up on that really quickly, and so it can be really a confidence builder. But I think that there might be a lot of different ideas that you can present to children. I mean, certainly they need to know how to multiply, but maybe some emphasis should be taken off of these algorithms to multiply and divide large numbers. And I found that geometry is very appropriate for children. You can make it hands-on, and the more hands-on you can make it, the better. And the Mobius strip is kind of an advanced topic, but if you can build it, I think it's appropriate for kids. Okay, like if you can build it geometrically. Students deal with sequences better than homework problems. Okay, like that student that was doing the geometric sequence 2, 4, 8, 16, 32, she could just go on until she wanted to stop. And at the bottom it says, I'm done, with a nice smiley face, right? If it was 30 problems that were all a little bit different and she got really frustrated at the 9th one, she's not going to say, I'm done with a smiley face. She's going to stop and still think she has more to do, right? So I think that if you're teaching arithmetic to young children, you might just say, hey, look at this sequence, look at this sequence, look at the Fibonacci sequence, or look at this geometric sequence, or arithmetic sequence, or, just have them think in terms of sequences, and then if they have to pick then every time they have to get the next number in the sequence, generally they have to do some arithmetic, right? So you get them to practice arithmetic without having a list of problems that they feel bad if they don't finish. And another great thing about a sequence is you'll never finish, right? Because it will go on forever. So it's like, yeah, you didn't finish, you couldn't. So there's never a sense of failure with that. Assessments are possible without tests. One picture kind of showed that a bit. And 1 week of class with support at home is sufficient. That's kind of what I think. I think for math education, I'm not talking about reading or writing or anything else, I think that really you could teach a child math once a week. And then maybe, have the parent go over with them, outside of a class or whatever. And I think that they'll have a better understanding of math than if they had to try to do the same problems 3 days in a row and were failing. So, well, that's literally kid stuff. Okay, so yeah, so let me check the time a little bit. So that's what I've been doing for arithmetic. Okay, so, and I've been doing it for a year, so that's why I've got so many pictures and all of that, or over a year. But I wanted to produce the college students that I want to teach, okay? I wanted to produce the students that made that I would expect, really, to see coming into college. And algebra is a love of mine, and thus I had a serious desire to design an algebra course. Okay, so I was doing all this arithmetic, but okay, how do we do this in an algebra way? And really what was going on at the time was I wanted to do a playground for arithmetic, and I wanted to do a playground for algebra, but I didn't know how to take students that have only been exposed to traditional methods of teaching and do a different way of teaching and have it work out. So I compromised with myself. It's actually just an algebra class, algebra course that I'm developing. So a little bit less of a playground on the algebra. Okay, so when I was developing an algebra course, I did so with specific principles. Guiding principles for an algebra class is I wanted the algebra class to include logic, okay? And when I say logic, I don't necessarily mean mathematical logic where you're doing second order predicate calculus or something like that. I just mean this, this implies this, implies this, implies this, therefore what is, just that kind of rigorous thing. So and then the type of logic I want to include in an algebra course would apply to proofs, okay, where you prove things mathematically. This is something that I think is lacking from most high school level educations and even early college math education. They're not really proving things. They don't really say why this is true or how all these rules apply these other rules or whatever. I think there's some appreciation that's lost when you lose those proofs. And notice I said some proofs, because I wasn't wanting to make like an undergraduate course where you proved everything from the get-go and you had to keep proving, right? I wanted to just, well, here's an example of a proof. Oh, and here let's do some more math. Oh, here's another example of proof. And then, just kind of get them in the idea of what a proof is. It's not supposed to prove everything. I wanted to more or less incorporate topics that a traditional high school would cover. I wanted a student that takes my algebra class to be more than prepared to go to college, but certainly as much or more so than a high school student. Geometry, since my thesis was in algebraic geometry, well, there's a little joke we have. An algebraist does algebra and works with students, works with symbols and variables and equations. And a geometer works with points and lines and planes and curves. And when somebody does algebraic geometry, they fail to tell the difference. It's kind of like the two subjects get merged a little bit. And that's said a little bit tongue-in-cheek, but I'm like, how can I teach algebra without bringing in some geometry? So that was my motivation or guiding principle. Motivate the material, motivate why. You want to learn this? Why is this interesting? Why is this fun? Why is this a good thing? Maybe the why is not that exciting. Maybe just the why is you learn this thing and it triggers that dopamine release that made you happy, right? And that's, or at least there's been studies that when humans learn new things, there is a dopamine release which humans find pleasurable. So I also wanted to open up the door to a calculus or analysis course. And from a mathematics perspective, these two words mean about the same thing. Calculus is kind of like when you first start learning it, and then eventually it's called analysis. So those were some guiding principles for developing an algebra class. So I found this book, Algebra by Gelfand, that I had the picture of earlier. And, well, I really wanted some geometry. And there's very few geometric pictures in this book. So I figured out a solution for that. Gelfand wrote a book on trigonometry. I'm like, oh, good, there's pictures and all this. And And we get some geometry there, we can talk about triangles. And it's very common that algebra and trigonometry are paired. So I was like, okay, I'll teach a class that's algebra and trigonometry, which I know other people have done. It's not that big a deal. But these particular books have particular qualities, and I like that they were both from the same author, because you didn't have to get used to a new writing style if you were a student. You had one author with the same author, right? So you can see how maybe that's a little bit easier. I wanted books that had some proofs. I wanted a book that had why questions. Why is it that when I divide 7 by 3 I get 1? Or what would happen if those types of questions. I wanted at least a few of those. This book has a sometimes conversational tone. There's sections in it. How to explain the Pythagorean theorem to your little brother or sister, right? So I thought that's pretty brilliant, writing a book to basically your younger brother or sister, saying how do you explain it to the younger brother or sister. So, and there's also a section, one of the students was reading ahead, how to really annoy algebra students, or something. How teachers really annoy algebra students. That's another one of the sections or something. So, but not every section is completely conversational. And this particular book provides nice questions. So there's a really good balance of the number of questions and the types of questions and all of that are asked throughout the book. Sometimes there's answers to the questions provided, well, actually a lot of the time. And it's not like 20 of the same type of problem that you need to solve 20 times, right? It's what if this happened? What if we did that? Would something be different if we changed this? Okay, and then, but not too many questions, okay? And one thing I wanted for a book was it's not too big, and I think the algebra is 100 or some pages, and the trigonometry, maybe it's 200, but there's a lot of pictures in it, and it just didn't seem like they were these big, huge algebra books that can be so intimidating. And it's ridiculous because algebra is not that big of a subject. I mean, you could. It is a big subject because you can always go into another topic and another topic and another topic. But those other books are so big because they're providing another example, another example, another, right? And there's a problem when you get the books too big. Where do you know, the person that's reading it, how do you know what's important and what's not, right? You don't need to know how to do the third example if you can do the second example, maybe, right? Because you can figure it out. So I really just wanted a book that taught the basics and didn't go too crazy. Okay, so the way I organize the class is it meets twice a week for an hour and a half. I really got fixated on this hour and a half. Feedback from the parents of the younger children is maybe an hour is better for their attention span. But an hour and a half for algebra seems perfectly reasonable, high school age kids. 2 months of algebra, and then the way I organize this is 2 months of algebra, 2 months of trigonometry, okay? And what's hard to say on the slide is it's 2 months of algebra, trigonometry, then algebra, that's where we are now. And then we'll have another 2 months of trigonometry, another 2 months of algebra, right? It'll go back and forth, okay? And that's the way I designed it. After I designed it that way, some people were saying, well, oh, I like geometry better. Oh, I like trigonometry better. So that way, if you liked one or the other better, you only had to wait 2 months. It'll change. And another reason I did this is I wanted to test retention, right? I wanted to give a full product that, okay, now you retained it. So if you did something else for 2 months and you still remember what we did 2 months ago, I got to kind of build that in. Okay, so the way I'm thinking it's going to roll out is it's 14 months total. So that's actually a long time, a year and 2 months. But that's kind of what I thought it would take to go through these 2 books at twice a week paced, without being pressured, having time to talk about other things that aren't in the book. I actually scheduled a test in May, and so this was the first test that's scheduled for what I'm doing. So I started in November, and the first test is in May. Okay. You can't do that in college because in May you've got another class coming, right? You can't start in November and then have a test in May, okay? But the reason why I wanted to have a test is to try to evaluate how what I'm doing would translate to a traditional setting. And the reason why it's so late is that I'm expecting the teaching I'm doing won't have a huge immediate payoff as far as taking tests, but I'm hoping it has a huge payoff, 7 months into it, or once you get all the reasoning and deductive stuff out of the way. That's my intention, that's my hope, but I'm going to give them a test, and it's more evaluating me, and it's actually going to let me know if I should just keep doing what I'm doing, or if I should make some changes in what I'm doing. I roll out the course 2 months at a time, so that way I can always adjust to what happened the last 2 months. Okay, and the students have asked me, I'll probably need to provide a linear algebra supplement for at least 2 extra months because of the textbooks. They don't really cover linear algebra at the depth I would expect at a high school. Okay, but that's fine. It's just a different subject. So if I wanted to have a full curriculum on algebra, I would include another book, right, and add on to the 14 months. No big deal. Okay, so one of the ways that this is organized is that I keep students, I always make students questions that I said they're king, and then they're high priority here. So I do this for my college classes, I do this for I've done this since Purdue, since I was teaching at Purdue. I always take questions at the very beginning. The class, of course, take questions in the middle too, but I always try to take questions on what they were thinking about since the last class or the homework they were working on or whatever. And so there's no reason to change it here. So I always ask for questions first, and I will completely derail the whole class if the if the students seem interested in further exploring the answer to a question. Okay, so here's my favorite slide in this thing. So students ask about, this has gone all kind of crazy ways, so let me just give you some examples. So students ask about infinite numbers, okay? In fact, young children will ask about infinite numbers. They'll know the word infinite. I don't know where they know it, but the parents must tell them about infinite. And so I actually was able to discuss infinite cardinal numbers with some high school students. And I think it was appropriate because they asked. Okay? It also was an excuse to talk about set theory. Okay? Now, I could have talked about infinite ordinal numbers, but I mean, there's a lot of things you can talk about when a high school student's asking about infinite numbers. They don't know what they're talking about, right? So I told them there was a difference, but the cardinal numbers are the first one I learned, so that's the one I taught. This is a really big question I've gotten several times. What are real numbers? When I got an undergrad in college and understood that maybe I was in calculus 2 and I understood I was using these real numbers, but I really didn't know how they were defined, that's the cruelest truth. That's the cruelest thing that math teachers do, right? They expect you to use these numbers and they don't tell you what they are. And well, one of the students I had picked up on it very soon in the course, and so he asked me basically what are real numbers, and similar questions have come up related to this question, what are real numbers? And I'm actually a little bit ashamed to say that I'm going to work it in to March-April section when we're doing some trigonometry, but this has been a really pressing question from a student. And perhaps it should be built into a regular curriculum. How can you expect people to use numbers they don't know what they are? And if you haven't taken advanced math, you probably haven't seen a definition of the real numbers. If you've heard of Dedekind cuts or Cauchy sequences, you may have. Okay, so, okay, this was a question. I thought this was a pretty innocent question. What does E equals mc squared mean, right? I'm not quite 100% sure of the context, but I might have been talking about planets orbiting and talking about the precession of Mercury or something, and mentioned how Einstein explained the precession of Mercury. And so I got this question. I think a student wanted to know the answer and just, oh, this guy might be able to answer it. And so I thought this would be an easy question to answer because E is energy, M is mass, and C is the speed of light. Okay? I think I've answered that completely. And so I told them this, and then you teaching, you kind of get an idea if they understand or not, and they were looking at me a little funny. I'm like, Well, and basically, to cut to the chase, I said, well, energy would be in joules. We could take this meters per second, that kilograms, and then energy would be in joules. You know what a joule is? They said, no. And so, well, now I'm trying to explain what E equals mc squared means, and they didn't. Now I'm trying to explain what a joule means. And so, a day and a half later, I think, one half of a class in the next class, I think I got a pretty good start on that question, but it sounds innocent enough, it really does. And I thought I just could say those words, but we had to go into measurement things. Cryptography, this is just something I'm interested in. I bring it up every once in a while. And I'm seeing students ask about it, because I just brought it up in the algebra classes. One student said, hey, can we do some more of that? And I'm like, okay, so we built it into the current 2-month algebra thing. Programming, one student really wants to know how to program. He was thinking he might not go to college. I'm like, well, then start programming. He liked computers anyway. And it's like, oh, well, start programming and you won't need to go to college. And he comes back 2 or 3 weeks later. He's like, you know, these other people are telling me that I don't need to go to college. I've been learning to start programming. I'm like, yeah, you're right. And it's true. It's true. People will hire you if you have skills. Imagine that. But anyway, so he has written some programs and emailed them to me, and I emailed him some programs back, but it's kind of hard to answer the questions in a class that's about algebra, right? Okay, so and this was a question we had, what's an example of a well-formed statement that can't be proven or disproven? And the actual question I was asked, is it too hard to give us an example? Right? And the answer is really yes, it's too hard to give us an example, but I gave them an example, and it was so helpful that I already explained infinite cardinal numbers, because there's a question that can't be proven or disproven about infinite cardinal numbers. So that's kind of neat. Okay? And so sometimes it feels like an algebra class is just an excuse to talk about advanced topics, right? I have what I want them to learn and all of this, but if something else comes up and they're interested and they're paying attention, well, we're going to talk about that, you know. Okay, so people who can answer these types of questions are not allowed to teach in public schools. And that's what I wrote on this slide. And then I thought it was a little bit harsh, because I actually did teach in a public charter school while I was doing this playground thing. But I was teaching outside of the school hours. But what I mean by this statement, even though it's not 100% true, is that if you have, a specialized degree and all of that, you probably were working on a specialized degree and didn't get the certifications for teaching. So then you wouldn't be allowed to teach in the schools regularly. Also, the way that economics is, once you have a specialized degree, then you've opened the door to lots of jobs, and so you've made it hard. The current way it's set up, it's difficult to attract people who would have a lot of other opportunities to education. Okay, but why should any student wait until college until someone answers questions like these? Okay? That's the question I'm asking you, right? A student asks, what's E equals mc squared mean? That's perfectly acceptable. It's all over the popular mindset, this equation. Nobody really explains it. It's perfectly reasonable to ask the question, right? I remember I asked the question to my dad, and he gave me E equals energy, M equals mass, and C is the speed of light. I think. My dad said, I think, so I had to say, well, did he know or not? Anyway, but there was I'll tell you a story here, okay? So when I was in 4th grade, I didn't like school, right? Why would I like school? It was long. I didn't want to be there. I don't like the people. Why don't we just go to recess? I didn't like school. And so I had a grand master plan. I'm like, well, why do you go to school? My 4th grade mind was reasoning through, well, why do you go to school? You go to school to get smart. I'm like, well, if I just prove to them that I'm the smartest 4th grader ever, they won't make me go to school, because then I won't need to get smart, because I'm already smart, right? So that was my reasoning. So now to actually implement this plan to be the smartest guy on earth, so I didn't have to go to 4th grade, was to ask the teacher who the smartest guy on earth was, right? Because that's who I had to be smart. And so the teacher said, well, I don't really know who the smartest guy is, and he's not alive anymore, but there was a guy, Einstein, who was pretty smart. So 4th grade, of course, my plan was not a success. My plan was not a success, but I got interested in Einstein at that point. So in high school, when I was reading Einstein, there was a symbol, I didn't know what it was. I asked my mom, what's this symbol? And she's like, I don't know. I'm like, well, I just want to know what it's called. It has to have a name. And so I didn't learn that was called a gamma until I was a sophomore in college. So why should we have to wait till college to get that kind of question? What's this symbol called? It's a gamma. It's a Greek letter under lowercase. You know, that's a pretty good answer to start off with. And then the gamma means whatever it means. But anyway, comparison to other curriculums. So this is my algebra course versus other stuff. Okay, 14 months versus 8 months in college. Okay, it's at high school level. It's drawn out. It's, you know, I have an extra 4 months to work with. Of course, with all the other enrichment stuff, I really want it to be a leisurely pace. This course is weak on linear algebra. I mentioned that. I might add a supplement to it. And that's something that's in the traditional high school curriculum that it wasn't in the book, and I don't want to add it into this book. I want to use a different book. There's no real Euclidean geometry found in high school in what I'm doing, so that would be something you might want to supplement what I'm doing with. And then I'm also thinking, I don't know if Euclidean geometry is as important as it was. I mean, there's a lot of other geometries that you might want to introduce at a young age, or maybe Euclidean geometry is not as important as it was. Now, we do the Cartesian coordinate plane and stuff like that, so maybe it is. But anyway, calculus optional for my students in high school, right? So that's the same. Functions are brought in outside of the text during the first trigonometry segment. Functions are a pretty big deal in mathematics. Technically, they're not in the textbooks I'm using. There's a concept, but I don't feel like it's really drawn home. So I have a day that I'm like, okay, let's talk about functions. And so I have to add that in manually. The intention is to empower students to be able to effectively read math writing. Okay? I've actually, early on, a student actually asked, how do I read this? And it really is a skill to read math, like you can read English or German or whatever. Reading math is a different skill than just reading a novel. Okay, I do think that. And my teaching mentor encouraged me to assume that undergrads can't read this book. Well, if undergrads can't read the book, the textbook of the algebra class or calculus class they were in or whatever, well, if I'm starting to think if kids can't read a book, if it's about math or whatever, well, they don't need to be in math when they're in high school. If they can't do very basic things, then they just don't need to be in math when they're in high school, right? I think that this is the one skill we should teach, literacy, right? And that's not what's being taught. It's how to do a problem and problem. Not, oh, let me look for books that have information about what I want. Let me take that information, let me understand that information, and let me apply that information, right? That's really where students should go. It shouldn't be about, I can solve this problem, that problem, this problem. And especially in the modern world, because computers can do calculations on rote, but they can't do the creative process yet. They may at some point, I don't know. Okay, what does this have to do with liberty? Well, after you have liberty, what are you going to do with it, right? So I'm a math teacher, I moved to New Hampshire, I want to have liberty, what am I going to do with it, right? Well, I'm going to try to do the best I can with it, and this is what I'm doing, right? So that's liberty right there. Are resources being allocated in an efficient manner? So can we have schools or educational things, or I don't care what you call them, that would actually produce more productive individuals in the future, basically. Critical thinking and deductive reasoning are important for self-sustaining, independent people. Information analysis. Although I'm not presenting some type of propaganda or anything, I'm teaching basic math, I think it's important for people who need to evaluate information that they might get from politicians or newspapers or something, and be able to deduce if there are logical fallacies in the paper or if their deductive reasoning is wrong or something like that. So the community in New Hampshire makes this possible, so that's a tie into Liberty. I mean, it's Liberty really is just a blank slate. You put on there what you want it to be. And because we have a community, we have some spaces that are arranged for multi-purpose use, and I'm able to use those spaces, and also the students that come by. And here's a question: are 20 to 50 child hours a week needed for meaningful academic achievement? Right, 20 to 50. I started out 20 to 40, but I'm thinking homework, right? Could even be up to 60 or 80, depending on the type of student we're talking about. And it's kind of ridiculous. The government's supposed to get rid of child labor. At the same time, the biggest utilizer of child labor that you can get, right? If the kid goes to a museum and learns something about things being hot and cold, I wouldn't call that labor. But really what schools are doing is close to labor. And it's the worst type of labor. It's a labor that doesn't have a satisfying result. It's just, I mean, you get an A, somebody likes what you did, great. You know, you take your work to the neighbor, they're like, they don't care if you added those numbers or not. And then here's the question, here's the big question. Who's gonna be the next Satoshi, right? Satoshi knew a lot of math, whoever this guy is, and he would have to know the math to do what he did, right? So why don't we have kids learn math now so that they can do great things and not tell us about it in the future. Okay? That sounds great to me. That sounds great to me. So thank you very much. There might be 3 minutes for questions, or 2? 3, 4 questions. Okay, good. Or 3 minutes. Okay. Perfect. Okay, are there any questions?
I was just going to make a comment because you were mentioning the time in school that eats up what the kids do dealing with math. And I was just throwing numbers around talking to some friends, and basically you're in school 180 days a year. Say you have, maybe an hour a day, but maybe less, if you're younger. So call it 100 hours a year just to make it easy. Say you start math, kindergarten, or even grade 1 to grade 5, you're looking at 500 hours of math instruction. At a school down in Massachusetts, when they start teaching math, it's only, when the kids are interested in it, there's no class. They had a bunch of kids approach a teacher, hey, we want to learn this math, we're going to take SATs, we're thinking we're going to go to college or whatever. So we put together this program, and in 10 hours, teaches kindergarten through grade 5 math, the kids pass the test and go. Right? 10 hours, or at the lowest possible end, 500 hours, right? And they're doing the rote memorization, in, out, in, out, in, out, going through the grade levels, all this stuff in their brain for a day or two, dumping it out. And we're still doing this. And so when I hear you talking about the amount of time, and you look at it like a labor issue, I mean, I just look at how ridiculous amounts of time is wasted teaching, not just math, but just teaching or so-called teaching in schools in general.
Yeah. And one thing I've done is also I avoid the summer breaks. So even though I say 1 hour a week, it's consistent instead of you break and then you just kind of I am going to take a 2-month break. But
have you looked at any of the available curriculums for homeschooling and have any opinions or anything like that?
Yes, some of them. I've looked at some of them. I pretty much have the thought of my own things because I really wanted to bring in a lot of geometry, and I don't know a curriculum that uses geometry the ways I want to utilize it. But basically I just make activities. The very first time I made an activity for 7-year-olds about modular arithmetic, which is kind of an advanced subject. It fell flat on its face. The students didn't learn it, so I haven't done it again. So I told the high school students something about modular arithmetic, and they liked it. So, it's just a matter of, I've been doing some trial and error with that, but I don't know, if there's a set theory curriculum for young people, I might want to do that, or combinatorics. So basically I just know what I know, and I know that certain subjects like combinatorics and set theory and things like that should be accessible at a young age, at least finite sets and some things, but they're not exposed to them. So I'm hoping that, I was thinking I'm going to have to redo what I'm just doing because I already have some 9-year-olds doing some algebra, but I was thinking that I would just avoid algebra until a certain age of reason or whatever, loosely speaking. And so maybe I could do combinatorics or some other types of computational type things, but I'm always adjusting to the feedback I get.
Yay, Darren.